Hello, Laurie.
Hey, how's it going? We had some technical issues this morning. It looks like everybody is here now.
Hi, Laurie. Yeah, we were starting to worry about you. Is everything okay?
We had technical issues. So
Yeah.
it took a little while to solve them, but here we are nonetheless. And
that's the most important.
you can see in here, that's good. All right. Someone's hands up.
I was just asking we're still going ahead.
All right. Well, we have two hands. If they were all asking if they're going ahead.
Yeah,
Hopefully the answer is yes, since Kurt is here, and the two of you are here, and I am here, so that's good. If there are other questions,
that question's answered. So it's good.
Kurt, how are you? You should have share screen capabilities and all that. And you're muted. Hey Juan, how's it going? I see your hand is still up. If you have a question that doesn't pertain to the webinar presentation, you can put it in the chat. Someone put something in Q&A. Same for me. Just started. I don't see anything. I don't see anything either. Same for me. Thank you. Kurt, how are you doing? It is a Monday after all, so who knows what happens to our computers over the weekend? Strange things usually happen.
Okay, can you hear me?
Yes, we can
hear
now,
you. Yep.
Yes.
I'm still working on my privacy setting.
Oh,
That seems odd.
We can run quickly introduction.
Zoom got reinstalled. Let me just try to share. Maybe it works. Share screen. And desktop 1, share. Grant access, open system preferences.
Yeah, maybe Mondays aren't the best day for webinars.
normally not for me either.
All kinds of things happened over the weekend when we're
This takes me 1 second. It should work. Okay,
No worries.
sharing is allowed. And you should be able to see my screen now.
It's not
nope.
come up yet, Kurt. I'm sorry.
It's thinking about it right now. Yeah, it's thinking
No, it
about it.
works. Yeah.
Yep, got it now. We can see your desktop.
We can see your whole desktop. So
Yes, I'm sharing my whole desktop.
all right, there you go. All
That
right,
looks great.
all right. I think we've managed all the technical bugs out of it.
Okay, we've got 107 people. Good morning to everyone. Do you need to introduce the webinar?
All right, go ahead, Eamon.
Yeah, we can have a short introduction in respect to time. So this webinar is dedicated to monitoring reservoir fluid movement during the energy transition for geothermal, CCUS, lithium explorations, and EOR++. So the control source electromagnetics method is a valuable tool for understanding reservoir fluids and their distribution. It's applicable in CO2 storage, enhanced oil recovery, geothermal exploration, and lithium exploration. And CSEM can be customized for specific reservoir goals by selecting the right components of the multi-component system. And with the interest of time, would like to present Kurt Strack to run us through this webinar. Kurt is the president of Energy Transition International and KMS Technologies, KJT Enterprises, a pioneering company specializing in integrated seismic and electromagnetic technologies for the energy transition. His expertise spans various aspects of the energy transition, including CO2 monitoring, geothermal exploration, enhanced oil recovery, and the integration of electromagnetic solutions to reduce carbon footprints. With this, we'd like to give the word to Kurt and to take us through the webinar. And thanks to Laurie and to SEG to organize this webinar. Kurt, please go ahead.
Good morning, everyone, and sorry for the snafus. We all are familiar with these issues when we give webinars. And it's getting worse with Zoom and Teams and whatever you use, having all kinds of problems. So I have made an outline for 45 minutes, and I will try to stay below that. I let the chair, Emin, interrupt me. So if you chat to him and you want something answered in the middle, it's no problem. I can cut it short so that we can stay within time. And I'll try to keep it simple today. So if you want more information, just contact me afterwards. First, I'd like to explain to you the background of what fluid imaging is and why we're using electromagnetics, in particular controlled source electromagnetics. And then I will give you some examples for geothermal, CO2 monitoring, EOR, and lithium brine exploration. There's no question that climate change requires the reduction of greenhouse gases, and CO2 is one of them. So everything that we are doing is geared towards reducing the CO2. So the entire energy transition is trying to bring us to zero footprint. And note, it's a transition. It doesn't mean we get rid of the oil industry. It simply means that we have to get the oil industry to zero footprint. To give you an idea about the markets, of course, we as scientists expected this, but it is finally happening that the geothermal market is going to be 80 billion by 2030. And the last Geothermal Rising meeting showed it to everyone. It was extremely vibrant and busy, and it was good. There's a totally new industry. Of course, since we are geophysicists or scientists listening to this, we realize that a lot of the people don't really know yet what's going on, but that makes it so exciting for us. The CO2 market, which is very important, the CO2 market being the CO2 injection market, will only be 10 billion by year 2030. And the reason lies in having to fulfill all of the legal requirements and be compliant from an environmental point. And we need to store CO2 safe. That means we don't want to get it back, and we don't want to induce seismicity, et cetera, et cetera. So we have to do a lot of geophysics to do this correctly. The enhanced oil recovery, or better said, enhanced oil recovery plus, that means we use CO2 injection to drive the oil out, can easily reduce the CO2 footprint when geophysics is used by 30 to 50%, almost within a short period of time. So this market is also very important to reduce the footprint, but also you can then capture the CO2 as you produce the oil. And we are doing this and replacing it with battery-driven machinery. And for battery-driven machinery, we need rare minerals or critical minerals, in particular lithium. And the first time I saw a lithium deposit was 1982. That resulted in me taking our magnetotelluric systems out of commission and trying to repair and calibrate them for a period of 2 years, because I couldn't believe that you could read this low conductivities. And now this is well accepted, and I will showcase histories for all of this. So what is fluid imaging? Let's first look at that a reservoir rock, and this is a picture of a clastic reservoir rock. A clastic means sedimentary, and we have here in orange the grains, and the fluid in the pore space, which is the space between the grains, is filled with water. We also can fill this with oil, and when we fill it with oil, we still have the grains water wet, unless we are producing too fast and are damaging the reservoir. I'm just throwing these terms in an explanatory fashion, so when you as geoscientists hear this, that you understand what reservoir engineers are talking about. So how do we measure this? We measure that in most cases from the borehole. That's not optimum because the borehole only covers 10 to the minus 13 of a reservoir volume of 1 kilometer cube. And what we routinely try to do is we try to measure from the surface and calibrate against the borehole. Well, that calibration is really, really important. And you'll be pleased to hear that today is the first time I show how we can certify the measurements from day one by calibrating against the borehole measurements. Now here is an example of an oil reservoir, and every hydrocarbon reservoir, because hydrocarbons are lighter than water, has a brine below. So I'm showing this because this links really to the CO2 monitoring. And the oil reservoir is very resistive, and this is the oil reservoir. And this is the water above and the water below. And we preferably inject CO2 into the brine part of the reservoir because brine, which is water saturated with salt, saline water of high salinity. It's important it's of high salinity because everything changes when it's of low salinity. Allows up to 66% CO2 dissolved in the brine. And that is quite important. That means we can inject a large number of CO2 in the brine without really damaging the fluid balance. If we increase the CO2 saturation above that, we end up with pockets and pressures and problems. So monitoring it is extremely important to maintain the integrity of the reservoir. We'll get back to that when we talk about the CO2. Now, the methods that are used to monitor these fluids mostly electrical methods. Seismic methods are not that suitable for fluid monitoring because seismic waves travel through the matrix, the solid part, predominantly, and electrical current is conducted through the water molecules in the fluid. If it's water saturated, there's more current flowing, fully water saturated. If it's oil saturated, the water content inside the oil will conduct it. Now, there are several techniques, and I use these names so that you have them when people talk about it. ERT, which is known as electrical resistivity tomography, is most commonly tested. It has very low resolution, it's depth limited, and it's highly inaccurate, but it works. I wouldn't say it works scientifically well. From an imaging viewpoint, you see something. It's a DC resistivity method. That means that the entire volume of investigation is between the current injection and the voltage electrode, so you have little to no volume focusing. Magnetotellurics, which takes the ratio between electric and magnetic fields, is better for larger depths, has very low coupling to resistors. It mostly looks at conductors, and because of that is limited. It's also limited because of the relatively low sensitivity. Controlled source electromagnetics could be the same as magnetotellurics. Some people call that CSAMT, but you do it controlled source EM to get a higher resolution. That means you bring your own transmitter, you do not take the ratio between the components, and you interpret each component independently, which you can do because you know where your signal comes from. So you get a better coupling. You can do good cross-calibration with logs. You get a better signal, and when you use a controlled source, a grounded dipole, you can resolve resistors as well as conductors. In fact, this is the reason of the growth of the entire marine CSEM industry, that controlled source electromagnetics can resolve resistors, hydrocarbons, which is also important for CO2. But I also will show you an example where controlled source electromagnetics resolves conductors. So it resolves both equally well. There are other methods. They are minor variation, and they just look at sweet spots. They're just mapping anomalies. And it's very important when you are in a drilling scenario where you actually spend a lot of money that you know the reliability and the risk in order to mitigate excessive cost. Here's an example for EIT. Essentially, you have a transmitter in a borehole and receiver in another borehole, and you're making a straight line between transmitter and receiver. You move the receivers up and get more measurements. You move the transmitter down, move up and down, and you end up with this grid. And each of the measurements gives you R equals voltage over the current that you inject, gives you a resistivity. You average the resistivity from all of these measurements, and you get an approximate image like described here. And that's why it is simple, it's commonly used, and that's why it's a poor resolution and only approximate. Magnetotellurics gives you a good picture of the subsurface, and as I said, it mostly sees, oops, I am too fast. It mostly sees resistors, and when you do controlled source electromagnetics, the same picture gets a little bit better unblurred, so you can say the improved resolution is about a factor of 10, just to pull a number out of the top of my head. So those are the three principal methods. The first example I give you is for hydrothermal, and hydrothermal is when you are looking for hot water, mostly for hot springs and greenhouse heating and things like this. So a long time ago, we carried out a survey in the entire country of Hungary, where geothermal licenses were available. And we defined in that about 42 drill targets. And I'm reporting about the first one that was drilled here only. Obviously, after that success, things became commercially political in Hungary. And the clients have contacted us 3 or 4 times in the last 10 years, wanted to restart something, but nothing has happened thus far. So we carried out magnetotellurics, gravity, and we integrated seismic, gravity, and magnetotellurics. I will only talk about the integration part here. You will find on our website plenty of publications on what was actually done here. The well was successfully drilled, and we were off by about 30 meters at 1,500 meter steps, approximately. And the well produced 4 megawatts of geothermal power from day one. Here is how we did this. The most important part in this application was actually the Hungarian geologist who took the old seismic, this is deep seismic data, and came up with a geologic model. And this is the well that was drilled based on our results. And looking essentially into an area with increased heat. And what that means, I will show you in the next diagrams. And this essentially gave the starting model. And I'm going to have to sit on my phone to get rid of that noise. With this starting model, the interpretation started. So we modeled the gravity and the magnetotelluric data, which we acquired. And you can see the MT sites labeled here. And I believe these are the gravity sites. And we found an area where we had a low resistivity anomaly. Low resistivity means we have increased water content in the rock, assuming the porosity is approximately the same. And increased temperature, and low density anomaly in the gravity. The gravity data was inverted and the MT data was inverted. Both were inverted very similar by looking at residual components, and it was done in a cooperative fashion. And then these anomalies where the low resistivity and low density coincided, that meant low density means more water and low resistivity means higher temperature. That made an anomaly. We then mapped those anomalies back with the seismic where we saw fracture zones, and then high-graded those anomalies where we had these two low resistivity, low density, and fracture zones into potential targets. Then before the drilling was done, after we had long done the report, the 3D models were rerun several times. Sorry about that. Were run several times, and then during the drilling, they went after this particular anomaly. And this is then when they found 4 megawatts. Another case history is from Saudi Arabia, and Ain al-Hara hot springs is along the Red Sea. Come on. By the way, this is Apple. The mouse always jumpy. Doesn't matter what type you have, but anyway. And we work together with the KFUPM, which is located right here, and they have a controlled source EM system. And as part of the testing and the support, we helped them carrying out this geothermal work, which is still ongoing. And the surface temperature of the hot water is 96 degrees. There's not that many people yet, but they're planning to develop that area as a geothermal area. Now, magnetotellurics works like getting the electromagnetic fields from the ionosphere, which is the magnetic field, or from the meteorological layer, which are here, lights, Arctic lights, and the high frequencies get absorbed near surface and the low frequencies go deeper. And when we have a low resistivity heat zone, when you heat up rock, the resistivity goes down. Then you can see this. So magnetotellurics often sees the deep source rock. And then if you get high enough resolution and you can beat the noise, you see the heat sweet spot accumulations above. You lay out a number of receivers, you take the ratio of electric over magnetic field, and you get an apparent resistivity, and these are tensor measurements because you lay out 5 components. And you can interpret it in 1, 2, and 3 dimensions. Now, in Saudi Arabia, because of the rough topography, and it's really rough topography, we also used other methods for static corrections. This is the layout, the magnetic field sensors, the electric field sensors, and the acquisition system. And we laid out a time domain system, a loop, 40 meters on the side with 10 meters in the center, and used those results for static corrections because the near surface effects of the electric field measurements can give you static distortions. And that was required in all of the measurements in Saudi Arabia. And you can see that here. This is a valley, and this is almost inaccessible. You can maybe use donkeys or carry the equipment up here. So people always ask, why are you taking lines directly along the valley? So somebody the PhD student took a cross line here, which is just another valley. But these sites are very, very difficult to access. So this has taken a long time to get these sites. And several years of studies, first geology, and there's lots of gravity data and seismic data. And so this profile from the west to the east, which you see here, is essentially seeing the hot spring. The hot spring is right there. There is a hot spring. From the west, yes, the hot spring is right here. You'll see a better picture in a second. And then the 3D inversion looks pretty much like this, where you have here the hot spring and you have local flow cells. And you'll understand by looking at the next picture why in the future we will be applying controlled source EM there to better understand this, because these flow cells that are postulated in here are very local and relatively shallow, and they can significantly change where you drill and how much geothermal energy you actually get out of this. And at the bottom, you may have the heat sources, but the heat needs to come up there through a certain fracture network. So here is the profile from the south on the left to the north west, and that is shown here. And again, you have the hot spring right here, and you can clearly see the fluid cell that you couldn't see in the 3D, the convection cell. And alone from this picture, you would say it would be a better location to drill here. And there is a plan to drill there and make a project which includes the drilling and controls OCM. But you know, it takes time to get all that funding in place. Now, the geologic interpretation was actually done 1 year before the field work, and the geologic interpretation already postulated this. And so all of these models thus far are very consistent. And so we are quite excited when that funding comes to continue that work beyond just the MT measurements done by PhD students. So in geothermal, EM is a standard method for geothermal exploration. It allows you detailed targeting, and resistive zones require CSEM. And you have resistive zones that have increased geothermal heat capacity in places like Iceland and basaltic rock, where you have chemical alterations making that resistive. There are many case histories in public domain. The future is to have better borehole tools, because existing borehole tools do not go to high temperature. The borehole tools pretty much stop at 150 degrees C, and maybe 8, maybe 10 hours. Of course, the service companies claim longer, but the logging is very limited in hot wells. The next example is addressing a carbon dioxide sequestration. That means that we are taking the CO2 out of the atmosphere. We are capturing it when we produce hydrocarbons or wherever we capture it. And we are pumping it into the ground. And in the ground, it gets sequestered. And of course, hydrocarbon reservoirs are ideal to seal a CO2 storage reservoir because the seal is there and then the CO2 doesn't come back. Now, another future area is to inject CO2 in basalt, because it is solidifying in basalt and thus will never escape, or also in crystalline rock, but that's not as common as the brine reservoirs. So what you do a baseline measurements. And in the baseline measurements, you get the background, and you get a background measurements. Here is displayed an apparent resistivity. And then you inject CO2. And after 2 years, the measured value in this case goes down. And after 5 years, you see yet another anomaly, which is the incremental part. And so mapping these anomalies is very important. Now, you can imagine, since the carbon credit business requires certification by the EPA or other government agencies, monitoring has to be very accurate and verifiable. So when we carried out the first test, one of the objectives was to deliver transparent data. That means that anybody can calculate the voltages that we have measured and verify that those are correct. That's number one. And number two, we tried to establish a correlation to the borehole. And I'll say a few words about that in the following slides. So what is happening is, and when you inject CO2, there are two issues with CO2. And the first issue is what happens to the reservoir fluid. When you inject CO2, the CO2 combines with the brine, with water molecules, and makes carbonates, and they become neutrally charged. So these are neutrally charged. They're bigger molecules than neutrally charged. We all remember that water is a dipole and has 3 electrons, and it's either positive or negative. So when you have a normal brine reservoir and it's mobile, you produce, these molecules move and the resistivity goes down. Any enhanced oil recovery, whether it's acoustic or electrical or force, reduces the resistivity of the reservoir significantly because you are increasing the mobility of the water saturated fluid part. And so in this case, when you inject CO2, you are increasing the resistivity. So a CO2 injected reservoir has an increased resistivity, not a decreased resistivity. So we are trying to map a resistor, but we are also trying to map where the water is. We are also trying to map a conductor. A second problem in CO2 is the seal break. And the reservoir seal is defined as the grain-to-grain contact between two different lithologies. The reservoir is in this case below. And when you push fluid through the reservoir, this seal, this grain-to-grain contact can break because of the stresses and strains you are exercising onto the grain-to-grain boundary. And every time you exercise anything on the grain, you are also exercising those same stresses on the pore fluids, which are right in between. So when it cracks and it breaks, you get a microseismic signal. And I'm also postulating, and we have observed that everywhere, we get usually also an electromagnetic signal before we see a microseismic signal. So when there is an earthquake, in most cases, we see an electromagnetic signal just before the earthquake, because you get that signal from the same forces acting on the pore volume. Now, monitoring usually requires a 3D modeling feasibility, and we go to the field and measure the local noise, add the noise to it, and optimize our sensor design and our spacing. And then when we carry out the survey to make sure that we maintain the quality of the data and the transparency, we carry out the quality assurance and support that with 3D modeling so that we then control the acquisition process by feeding back overnight to the field crew whether they need to move the equipment or whether it needs to stay a little bit longer to get better data. The processing and evaluation is done very carefully because the error needs to stay less than 0.5%, and this is 0.5% between the beginning and between the end of the survey. And again, this is supported by 3D modeling. And then before you do a repeat survey, you address those weak areas and you optimize the acquisition for a time lapse. Once you start monitoring, generally, let's assume a 10-year life cycle of a CO2 reservoir, then this monitoring will go on for 10 years, and you do not want to have too many changes in those 10 years. So that's why this predictive optimization is important. You saw this. I'll go back again and start it again. So now we are injecting a current, and the current which goes from here to here is perpendicular to these current density lines and goes downwards and outwards with increasing time. So we inject the square wave current through a transmitter. We lay out a bunch of receivers. In practice, we use the same magnetotelluric system that we use overnight to record magnetotellurics, and during the day we do controlled OCM. But in this case, because of the low temperatures, that was minus 25 degrees C, we actually had a 24-hour operation, simply because I was really scared to turn off this 200 kilowatt generator in the evening and then turn it on in the morning again after it sat there for 10 hours at minus 25 degrees C. And these are the receivers and some pictures from the field. And you can also put shallow borehole tools down, which go up to 100 meters to measure that component. There are some advantages to that. Now, in North Dakota, we used 4 transmitters at 2 locations, both cross dipoles. We used both directions in order to see anisotropy and structure in the data. The injection site is near a power plant. There's a big power plant here. A lot of this is a lignite mine, and they need to have the carbon credits and inject the CO2, or they need to shut down the lignite mine. So it's very important for them to develop this. there is a potential site back here, but there also are some wells here. So this is why we made two lines like this and connected them. Whereas the reflection seismic covered the whole area as a grid, and they spent tens of millions of dollars on it. And this cost, this whole survey, including interpretation, cost about 900,000. So just to give you a factor of at least 35 to 40 cost difference. Now, these are the composite resistivity logs from several wells along here. And we built an anisotropic model out of it, which has 31 layers. The vertical resistivity is in pink, in blue is the horizontal resistivity. And these are not obtained by averaging. We are using the total conductance for the horizontal resistivity and the cumulative transverse resistance for the vertical resistivity. And we verify with 3D modeling that the equivalent 31 layer model is within 1% of the individual data points. The reason why we do that is because using all of the individual layers would become prohibitively expensive in computation time. Even for this small survey, the 3D modeling feasibility takes at least 2 to 4 months. We then have a 3D anisotropic borehole log, which we can then use to verify everything against. The horizontal blue lines are the seismic horizons, and we honor those when we average this. So in addition to the sensitivity-based averaging, we are also honoring the seismic horizons so that we can maintain that reservoir. In North Dakota, the two injection targets are at 1.6 kilometers and 3 kilometers. The deeper one is at 3 kilometers. The resistivity values are displayed here. Again, some equipment shots, but we did magnetotellurics for the background resistivity and CSEM. The magnetotellurics, we did 42 stations every 600 meters. The feasibility told us we needed 200-meter spacing for the CSEM, so we had 124 stations at each station, 5 components. So times 4 sources for each of the stations, so it's 4 times 5, 20 times 125, so easy 2.5. We ended up with different transmitter waveforms with 3,500 independent soundings and inversions, which told us that we had to have a different way of interpreting the data, which was totally data-driven and automated instead of driven by the brain of a single geophysicist. Here is the results for the magnetotellurics. On the left side, you see a single site processing. These are the quality assurance one. That means these are the 1D inversions. As reference, we have the horizontal part of the 3D anisotropic borehole log here. And you can see it matches nicely. But we do have a mismatch between the inversion result response in the solid line and the data here. So we applied a remote reference processing. We had 2 remote reference sites, one in 300 miles away north of it in Grand Forks, and one in Austin, Texas, a few thousand miles away. Both gave the same results. And you can see when you do remote reference processing, this anomaly is gone, which is lower frequency noise. And the match between the log and the inversion is even better. So we were very confident that this data was good. We then did the 3D inversion of these 2 lines. Here's the cross line. And you can see some deeper structures, but this is mostly to get the background. And the data gets shipped directly from the receiver to the cloud. We move this a little bit away to get it away from the analog parts to ship the data without any interference via the cell phone network. The controlled SOCM, which gives you more accuracy, this is only 1,200 meters of profile section on, I believe this is line 1. And You can see here the injection reservoirs, and this is the seismic, and it matches the seismic. All of the parts of the sections that we tried matches. Notice there's a mismatch here. This is because these are unsupervised inversion. That means there's no human interaction. The inversion starts with a half space and runs totally automatic, only using the data weights to influence the inversion. And they give very consistent results. We tested that we had the sensitivity at depths. I skipped that in the interest of time here. So here we compare the 2D MT inversion of the same section with the section I just showed before. This is just a little bit lower resolution. But you can see here, if this is the MT with 2 sides, and this is the CSEM, it gives you more detail in this area. We then included the seismic horizons into the 3D model and calculated for each side the response. And the dashed line is the response, in this case, for the electric field EX, EY, and the vertical magnetic field dB dt, dBz dt. And this is the reservoir response. So we are only interested in this part. And we can see that all of these components match the field data from the 3D response, which is quite impressive. The X field gets noisy earlier because it's lower, about half the amplitude of the Y field. That is related to the symmetry because the X field is in the same direction as the transmitter dipole. So if you use an east-west dipole, the X field is the east-west one. If you use a north-south one, the X field is a north-south one. And we see this consistently throughout the survey. And so we feel very comfortable that everything matches. And we feel like we can now say that the data itself is certified by the 3D anisotropic log, which is the ground truth. Obviously, being a geophysical measurement, if the log gets improved and changes, we have to go through this process and see within what confidence we can match then the change situation. I have essentially given you the summary before I came to this slide. So the future for CO2 monitoring is to deal with the noise near the injection site, because obviously the injection hardware will generate a lot of electromagnetic noise. And we need to be more accurate with the focal point of the imaging, just like migration does in seismic. And that's why we measure multiple electric fields, and we actually have already the data to do this. We just haven't done that part of the imaging. The next example is for a water flood, and we are mapping a conductive anomaly. And I picked this because it's a conductive anomaly. And we did the same process as in North Dakota. We did a 3D feasibility. We did noise measurements. Here, we actually took an MT system to the side, and we measured MT, and we determined that the geology was layered. Beautiful site. We started out thinking that there's no possibility to find a site. Then we found a site. We found a well, we found a reservoir. We built the equipment custom built for this purpose. And then the objective is to see the water flood. This is a generic layout. In the field, there was only one line because there was only one test line done. And you have an injection well here, and these are producing wells, and you lay out a bunch of receivers across the flood front. And you're hoping to see this flood front because it allows you to optimize your production. You essentially can shut down your injectors before the water breaks through at the producing wells. Once the water breaks through at a producing well, it costs you $500,000 to work over that well and complete it again. So you do not want the water to break through at any production well. You want to know where the waterfront is. We also recorded seismic data here. We didn't interpret it, and I just show you the results for the magnetic field. Processing is standard. We did the typical digital signal processing, pre-stack, post-stack. A lot of filtering done because the data was very noisy because it was an experiment. And then a lot of interpretation done to get to the results I'm about to show you. Here's some data. This is the current. These are the electric fields. This is the magnetic field. After signal averaging or stacking, the electric field looks like this and the magnetic field like that. the transmitter was in this direction, the water flood was here, the water was injected in 2-kilometer steps from a horizontal well that was drilled from about 4 kilometers away. So there was no well directly nearby. This is the center receiver, and this is the 400-meter away receiver at the edge of the line. These are the 3D modeling results, and these are the actual measurements. So where the water was injected, we got after 2 days an anomaly of 30%. And this is the reservoir changes as we predicted them. The reservoir changes are between 0.1 seconds and 1 second. And 400 meters away, I would not say, when I look at the data, that this is an anomaly because it's noisy and only 2%. But knowing where the reservoir is, we probably still see something. And the 3D modeling sees in both cases a much stronger anomaly. And we had no explanation for that. We now understand it because we compared notes with other companies doing similar things, multinational oil companies. And they say it's the casing. And we say, no, it's not the casing. We modeled all the casing. There are dozens of casings nearby. And the casing doesn't give you the anomaly enhancement. So what we think it is that this current gets channeled into the water flood. And since they're pumping 8,000 liters of water, I think every hour into the ground, it's a large amount of water. And so the electrical current is essentially channeling in here, which gives you an anomaly enhancement, which is the only explanation that we can find. And that seems to be making sense. The result is that CSCM clearly sees a conductive anomaly. In this case, we have to add borehole measurements and build the linkage. Next, we will address lithium brine. In Nevada, EM is standard, in particular in the Railroad Valley. That's the place where I looked for geothermal 1982 and 81, 82. And we stopped and thought our equipment was not working because we could not imagine to find a 0.30 meter conductor at 1 kilometer depth. That's ocean, seawater. There is no ocean at 1 kilometer depth. In Sweden, where they are now moving villages to mine the lithium, electromagnetics is a standard tool. Argentina, part of the Golden Triangle, Chile, Argentina, Brazil, electromagnetics is extremely successful and they're mining it. And in Saudi Arabia, we did several tests with our client. We are postulating that there is a deposit and hopefully that will be followed up and eventually drilled. So what's happening with lithium brine? You need a salar, which is nothing else than a dry sea, like the Salton Sea in the Imperial Valley or the Dead Sea in Israel. And what you also need mountains. You need the minerals from the mountains. If you don't have the minerals from the mountains, you do not have the mineral condensation. Well, it's not a condensation kernel, but we all know that rain only happens with the aerosols in the air. That means you have to have dust in the air where the water can collect. So here you need to have minerals where the water can evaporate and the electric charges can collect. And these minerals must be the right type of minerals that they can actually hold electric charges. And lithium is one of those minerals. And so when you have this coming from the mountain range, then you are essentially accumulating in lithium brine, and this lithium brine can then be used to build batteries. And you can see here, Chile, Argentina and Brazil are part of the Golden Triangle. China has large lithium, Australia, the US is right here. And now you have Portugal, but Sweden is also coming up there very fast. There are two examples I'll show you done by a colleague of us. She's also co-author on the paper that I'll give you the citation at the end. And they're both from Argentina, the first example. And what we can see here is that the low resistivity is blue, and you can see strong low resistivity layers and you have about 3,300 meters. You have them 3,500 meters. So you have them at about 400 meters. And you have essentially, these are the lithium brines. And the same here. This is another example, all drilled, and they're very successful. They keep going. Here again is the lithium brine. This is about 400 meter steps. And you have some other low resistivity anomaly right here. And then this is more resistive, and then this would be the lithium brine. Now in Saudi Arabia, if you remember the map from Saudi Arabia, we have a test site near Daman and a Half Moon area, and then we have another test site near Riyadh. And in both cases, we see very similar results. We have MT measurements, and the MT measurements see a conductor of 0.2, 0.3, between 0.3 and 0.4 ohmmeters at approximately 2, 3, 4, 500 meter steps. And these are the CSCM response from the same side. And you have the two different CSCM models. Somehow the MT model is not displayed on this. This is my mistake, because it started with the nah. So, but you see also in the CSCM model, come on. You see a very strong conductor right here, which is approximately the same depths. And so this is the MT model. These colors are wrong. So this one is the MT model, and this one is the CSEM model. It's just a flip on the color scale. And you see a similar low conductor, not quite as low as in the MT, but you see this conductor essentially matches, and the conductor has to go more down than it is here. So lithium deposits are extremely conductive. The hardware requires extended dynamic range. We are applying tricks in our amplifiers that we use for controlled source EM, and they give us also the advantage of being able to deal with larger dynamic range in magnetotelluric signals, which is the reason for the performance. And in the future, the system has to be made for better use in hostile environment, because most of these lithium environments are really unpleasant, hostile deserts where it's almost impossible to drill holes. So we'll have to address a lot of these operational issues to be able to record the data more efficiently. And last but not least, I'll invite you to look at the recently published paper, which summarizes all of this. And Cesar, my co-author of this presentation, is the senior author there. Anna did the lithium, and Pantelis did the lithium in Saudi Arabia and the geothermal. Yadinia did the interpretation, and Andri did the acquisition for North Dakota, both MT and CSEM. So all of the guys are on here. And with that, I'll open the floor for any questions.